Yeah, it started.
Yeah, I think it started.
Okay. So Rohini, you can start.
Yeah. So good afternoon, everyone, and welcome to the weekly online lecture series on atmospheric dynamics and its applications to climate sciences, which is jointly organized by Savitribai Phule Pune University and South Asian Meteorological Association, SAMA. Today is the lecture number 10, and it will be delivered by Dr. A.K. Sahai from IITM. He's retired from IITM Pune, on equation of continuity in Cartesian and Isobaric coordinate system, Dine's compensation principle, concept of level of non-divergence. But before we go to the lecture, I would request Professor Ajit Tyagi sir to deliver the welcome address. Sir, you are muted.
Mute. You're mute.
Thank you, Rohini, and I extend heartiest welcome to all participants. And special thanks to Dr. Sahai for having agreed to deliver this important lecture. Dr. Sahai is one of the meteorologists who has got a good grip on the basics and also the applied part. He has developed many operational products for the India Met Department, but he has got very good foundations as far as the neural networks and application of them in the meteorology. And also we are talking now of AI and machine learning, but he was familiar with these concepts in the early part of his career also. So he's a practical man, and today's topic and our lecture series itself is a basic concept of dynamics and its application to weather and climate sciences, and there wouldn't have been a better expert to deliver a talk. And today's topic also is very simple but very important. Cartesian coordinate continuity equation. These are the basics and on which foundations entire dynamics works. So I'm happy that Dr. Sahai will be delivering lecture. He expressed his little hesitancy that he has not delivered online lectures for quite some time, but his vast experience and he delivers talks in the scientific events. So I'm sure he'll be able to do a great justice in today's lecture also. And I request all participants to pay full attention. And this is a very important topic and basics. And feel free to ask him during the question answer session. So once again, thank you, Dr. Sahai, for having agreed to deliver this talk. And we wish a very, very positive and interactive session today. Thank you.
Thank you, sir. Now I request Dr. Swagata Paira, BIT Mesra, to please introduce our speaker.
Yeah, so are you sharing the slide?
Yes, I'll share.
Thank you, Dr. Rohini. It's my great privilege to introduce Dr. Atul Kumar Sahai, Consultant National Monsoon Mission Scientist, retired as a scientist G.
Display full screen, Rohini.
Rohini, full screen, yeah.
Yeah.
Dr. Atul Kumar Sahai is a retired scientist from the Indian Institute of Tropical Meteorology, Pune. Before joining IITM in 1996, he obtained MSc in Mathematics and a PhD in Science from the University of Allahabad. His areas of expertise encompass climate variability, prediction and modeling, as well as tropical convection, monsoon dynamics, extreme weather, and the application of AI/ML in climate science. Dr. Sahai's research has yielded approximately 180 papers with an impact factor of 450 and nearly 4,800 citations. He has delivered over 200 invited talks and supervised 12 PhD students. Dr. Sahai's pioneering research contributed to the development of the dynamical ensemble extended range prediction system, which has been operational at the India Meteorological Department since 2016. 180 papers with an impact factor. Some months, okay. This system provides 3 to 4 week weather forecast, aiding in the prediction of the Indian summer monsoon and associated extreme events. He has also devised strategies for leveraging these forecasts in agriculture, hydrology, and disaster management. He has rendered his service as the project director of the National Monsoon Mission and High Performance Computing and coordinator of the India-UK Water Center. Rohini, the next here. In recognition of his significant contribution to research and services, Dr. Sahai has given responsibility to serve as the head of climate research and services at IIMD for 2 years. During this time, he played a key role in integrating IIMD operational forecast with the global framework for climate services and establishing a regional climate center. Dr. Sahai has received several prestigious awards, including the IITM Silver Jubilee and Golden Jubilee Awards, as well as Certificate of Merit from the Ministry of Earth Sciences and Fellow of Indian Meteorological Society recently. He has collaborated with numerous national and international institutions and has served on various expert committees of the World Meteorological Organization, including as a member of the WWRP Scientific Steering Committee. In addition to his research, Dr. Sahai has been an advocate for the advancement of meteorology through the Indian Meteorological Society. He served as a chairman of the Pune chapter 2014 to 16 and vice president of the National Council for 2 consecutive terms, 2018 to 2022. Welcome, sir.
Sir, I
Thank you.
request you to please. Yeah.
So actually, when I was, first of all, let me thank SAMA, Professor Ajit Tyagi, Professor Das, Dr. Tyra, Rohini, for giving this opportunity. I must confess that when I was contacted to deliver 2 lectures, then I was slightly reluctant actually that I may not something happened to this.
Sir, we can see full screen.
We can see full screen, even your voice was stopped little bit, but now it is fine.
You can see full screen, but I am
Yes.
not.
Oh,
Very visible to me also.
If you wish, we can.
Huh? Let me again share.
yes, sir.
Okay.
Yeah.
Stop share. Share.
Rohini, do you have the backup file?
Nahi, no.
No, what is happening? Okay. So now you can see
It is coming. Yeah.
2 things are coming or only 1 thing?
Only
One.
Okay, fine. So I was asked to deliver 2 talks, but I have not given classroom lectures since last maybe 15-20 years, though I have given many scientific talks. So I was a little bit reluctant, but then I have taken it, okay, let us see how I can do the justice. So the topic of my talk is equation of continuity in Cartesian and Isobaric coordinate system, and then Dine's compensation principle and level of non-convergence. No, it is not moving. Yeah, now it is. So in this, I will cover Lagrangian and Eulerian frame of reference, total and local derivative. Actually, what happens when a person is given isolated topic, then he has to again go into this Lagrangian, Eulerian, total and local derivative. I know that many people, those who have given lectures on different equations, maybe equation of motion and this, they have already discuss this, but again, since I have to do this, so I will slightly touch them. And then equation of continuity in first Cartesian coordinates, and then I will give in generalized coordinates, and from that I will see how to give the equation of continuity, derive the equation of continuity in isobaric coordinate system. And then Dine's compensation principle and the concept of level of divergence. So equation of continuity is just conservation of mass. So it is, we know from many this that mass can neither be created nor be destroyed, although it may be rearranged in space and time. So this is what, and this principle is used in deriving equation of continuity, the mass conservation, which is used in understanding several phenomena related to transport of matter, especially fluids. And this transportation of fluids happen from one region to another, and hence determination of instantaneous values such as fluid velocities are often important. So in this regard, the continuity equation is one of the various fundamental principles of physics used for the analysis of the uniform flow of fluid. So, but as I told you, before deriving equation of continuity, let us understand Lagrangian and Eulerian frames of references and relation between total and local derivatives. So, a given fluid flow can be sampled in two quite different ways. One is tracking specific parcels, that is called Lagrangian, and the other is observing motion of fluid parcels that flow through the fixed. So we assume that there is a fixed volume or something, and that through this fluid parcels are flowing. So this is the Eulerian concept. But in Lagrangian concept, we have to follow the fluid particles. So suppose at instant time t, this is a control volume of mass m, and this is ds is the volume, and which are having 10 fluid particles. So what will happen at time t plus delta t if we are following Lagrangian material volume? So this volume will always contain those 10 particles. So the volume will be deformed in this form. And then we have to follow the motion, and we have to catch these particles already. So, but when you are dealing with Eulerian, then you see now there are only 5 particles, then 5 particles have left. So other particles are coming and going. So this is fixed at a place. So this is the Eulerian concept, and the fluid material inside the control volume is continuously changing, assuming that there is some fluid flow. So the usage of Lagrangian and Eulerian is standard. If no such label is appended, then by default we think that it is Eulerian for almost all cases. Now, Lagrangian methods are often the most effective way to sample a fluid flow, and the physical conservation law, because the law of physics, Newton and mass and everything, that is for a particle. But when we are so Lagrangian, you are following a particle, so it is very easy. So they apply to moving fluid volumes rather than the fluid that happens to be present at some fixed point in distance. But the Lagrangian equations of motion applied to a 3-dimensional continuum are quite difficult in most applications, and thus almost all of the theory in fluid mechanics is developed within the Eulerian system. But they can be used side by side to understand. In order to apply the basic laws in Eulerian frame, it is necessary to derive the relationship between the rate of change of a field variable, which is following the motion. That may be called as substantial derivative, total derivative, or material derivative. And another is the rate of change with respect to a fixed point, that is called a local derivative. So how they are related? So suppose the temperature measured on a balloon. So balloon volume, the air parcel is fixed, which moves with the wind is T. Temperature is T at the point X, Y, Z and time T. For the air parcel within the balloon, the location X, Y, Z is a function of time. So X is a function of time, Y is a function of time, Z is a function. But following the balloon, T may be treated as truly a function of time, and its rate of change is just the total derivative dt upon it. If the balloon moves to a point x plus delta x, y plus delta y, z plus delta t in a time delta t, so t plus delta t, now is the time, then the temperature change recorded on the balloon delta T, capital T temperature, that can be expressed as a Taylor series like this. Delta T is equal to dou T upon dou T delta T plus dou T upon dou X delta X plus dou T upon dou Y delta Y plus dou T upon dou Z delta Z. And plus higher terms where delta T, delta X square and delta Y square and other things are there. So since it is a small infinitesimal movement, so higher terms we can neglect. And then if we divide it by delta T and limiting delta T tends to 0, then left hand side will be dt upon dt, and this will be dou T upon dou T plus dou T upon dou X dx upon dt, and this, so which dx upon dt is nothing but u, dy upon dt is v, and dz upon dt is w. These are the components of wind in x, y, and z directions. So using vector notation and rearranging this, we can write dou T upon dou T is equal to dt upon dt minus u dot del T, where del is the differential operator I dou upon dou x plus j dou upon dou y plus k dou y dou z, where I, j, k are the perpendicular to each other along x, y, and z direction, the vectors, and u, capital U is ui, vj, wk is the velocity vector. So the term minus u dot delta t is it is called advection, temperature advection. So it gives contribution to the local temperature change due to fluid motion. So this is the total change, and this is the advection, that will be the local change. So this is how this total derivative and local derivative are related, and this t can be any variable star, and it may be like this, and u further can be this bifurcated into horizontal and vertical. So w and uh is ui plus vj. So now if you want to derive continuity equation in Eulerian frame, so let us assume a volume of side delta x, delta y, and delta z. So the volume will be delta x into delta y into delta z. That is fixed in a Cartesian coordinate frames. For the control volume, the net rate of mass flow through the sides must equal the rate of accumulation of mass within the volume. So if we are only taking the side which is perpendicular to x-axis in the yz plane, so here is from A the fluid will be entering, and from B the fluid will be going out. So if rho is the fluid density and u the fluid velocity component in x direction here at A, then the rate of inflow of mass per unit area through A is rho. Now, what will be the rate of outflow at B? So u will be, so dou upon dou x rho u is the change of this rho u multiplied by the distance delta x So, and added it to rho u. So this will be rho u plus rho upon rho x rho u into delta x. Now, this area of phase A and B both are delta y into delta z. Therefore, net rate of flow into the volume element due to u component is rho u delta y delta z. And since this is inflow through A and this is outflow through B, so we will put minus sign to this. And rho x, rho u, delta x, delta y, delta z, because rho u, delta y, delta z will be cancelled out. So that is the net accumulation of the fluid in x direction. Similarly, you can see this will be in the y direction and z direction. So the net rate of mass flow in the control volume, if we add from the all three directions, then it will come at minus rho minus del upon del x rho u plus del upon rho y rho b plus del upon del z rho w multiplied by delta x, delta y, and delta z. So this is the net rate of mass, which is the increase, you can say, in the control volume. And now this will be equal to, the same quantity will be equal to, if you see per unit volume, so you have to divide by delta x, delta y, and delta z, and this quantity will be minus del dot rho u. Now this must be equal to the rate of mass increase per unit volume. So this is the accumulation, net accumulation. So this will be equal to the mass increase. Now the increase of mass per unit volume is the local density change, that is d rho upon dt. So therefore d rho upon dt plus, because this will be equal to this, so when it will come to left side, this will be d rho upon dt plus del dot rho u is equal to g, which is the mass divergent form of the continuity equation. And alternative forms can be written like this. And this is, you can say, the Eulerian equation of continuity for the compressible fluid in rectangular Cartesian coordinates, which we have derived through Eulerian concept. Now we will derive the same equation from the Lagrangian concept. So suppose this parcel delta x, delta y, and delta z and rho be the density, then the mass of this fluid in this parcel will be density into volume, that is rho into delta x, delta y, delta z. So the conservation of mass of this parcel, so the mass of this volume will be, mass of this parcel will be d upon dt of change of this with respect to time is equal to g. Now this is when we apply the chain rule or of differentiation, so we will get four quantities, delta x, delta y, delta z, d upon dt rho, and like this. So we denote it as equation A. Now let the velocity of the fluid parcel is denoted by u, capital U, that is u e w in xyz direction, and assume the shape and size of the fluid parcel in a flow. So whatever fluid parcel we have taken, that is continuously changing in time. So now suppose this side A has moved to A dash and B have moved to B dash, but A dash is slightly more, you can see here, B is slightly less. So both sides are moving in its own way with its own velocity. So let the surface area of the fluid moves to with velocity UA to A dash, and B moves with velocity UB to B dash. Then the rate of change of the length of the fluid parcel in the x direction is d upon dt delta x. So change in x direction. That will be UB minus UA. This is your velocity that change in length in x direction. So U and UB is UA plus change in U at A delta x, dou x into delta x and minus U. So this will be cancelled out and you will get, and then you divide it by delta x. So 1 upon delta x d upon dt delta x is equal to dou U upon dou x. So similarly along y and z direction we will get these equations. So this we denote as B. So now this is, so far we got this equation A and equation B. We have derived this. Now dividing A by rho delta x, delta y, delta z and using B, we will get, so here it will be when you are dividing by this, in the first term of A will be 1 upon rho d upon dt rho. In the second term, it will be 1 upon delta x d upon dt delta x, like this. And then you use 1 upon delta x d upon dt delta x and these terms from B. So this will be 1 upon rho d rho upon dt plus dou u dou x plus dou v dou y plus dou w dou z. And this is nothing but 1 upon rho d rho upon dt plus rho dot u is equal to 0. This is the same equation which we have derived using the Eulerian frame. And this equation is applicable to all type, because this is the mass conservation. This is applicable to all type of fluids, compressible, incompressible, viscous, steady, laminar, turbulent, and so on. Now, for a steady flow, dou rho upon dt equal to 0, and hence equation 1, which we have derived earlier, first term will be 0, and we will get only this. But you have to again, this will be multiplied to this, and then you will get delta, because rho is only steady. So it is with respect to time, it is 0, but not with respect to x, y, and z. And when the fluid is incompressible, then rho is constant. Then all it is constant means with respect to t, x, y, z, all it is constant. And then you will get dou u upon dou x plus dou v upon dou y and dou w. So these are in a special cases when we get continuity equation for steady flow and for incompressible. Now we have to derive equation of continuity in isobaric coordinates. So sorry. So so far we have seen that height, that is z coordinate, or the distance from the Earth's center r, we have used, but this is not the mostly, for many cases, this is not convenient vertical coordinate, particularly for mathematical modeling. So there are several coordinate systems which are more or less, they are peculiar to hydrodynamics and particular to meteorology. So the essential feature of these systems is the replacement of vertical coordinate by pressure or logarithmic of pressure upon surface pressure, or pressure normalized with that is sigma coordinate, or potential temperature or so. So different things are, so each this vertical coordinate system, how is the problem in our hand, we have to decide based on this. So before deriving equation of continuity in the, we have to derive in isobaric coordinate. Let us derive in the general vertical coordinate system, and then we will derive it in this. So consider a general variable A, general vertical coordinate R, which is assumed to be a monotonic function of height z. So when we are replacing z with some other variable, so z we assume that is a function of that r, and x, y and t. So z is a function of x, y, r, and t, and a is now, which was earlier x, y, z, t, has become like this. So the vertical partial derivatives in the new and old coordinates. So dou a upon dou r is the new vertical coordinate system, will be dou a upon dou z multiplied by dou z upon dou r. Or similarly, for the old in z coordinate system, dou a upon dou z is equal to dou a upon dou r into dou r upon dou z. So this we will use in further derivation. And if we want to, for any partial differential with any other coordinate, s, suppose s may be x, y, t, any one of this, because z we have already seen. So dou a upon dou s in the fixed, when r is constant, will be equal to dou a upon dou s when z is constant plus dou a upon dou z multiplied by dou z upon dou s when r is constant. And this can be written from equation 1, dou a upon dou z. This, if we replace it by this, we will get the equation 2. And now we can put any variable. So we have got this equation 2. So s can be x, y, z, and x, y, and t. So if we are putting t, equation t will be like this, which can be further written as dou a upon dou t z constant is equal to dou a upon dou t r constant minus dou a upon dou r into dou r upon dou z and dou z upon dou t r constant. Similarly, for x and y, we can write this. So this we have derived in from z coordinate to general vertical coordinate r. Now we can also write horizontal gradient of a scalar a. So in the z coordinate, del z a is equal to del r a, and then of r with respect to z, and del r z. So here r is fixed, del r means r is constant, del z means z is constant. So where del z a is equal to only I dou a upon dou x plus j dou a upon dou y, z equal to constant. So we have split it into horizontal and vertical coordinate. Similarly, divergent of vector b, because this is a scalar, this is divergent, we can write like this. Again, b is equal to horizontal component of u velocity, that is iu plus jv, and we can write like this. So the vertical velocity in height coordinate w can be expressed as w is nothing but dz upon dt. And dz upon dt, total derivative of z, can be written like this in your generalized coordinates. And we will get r dot, where r dot is dr upon dt is equal to dou r upon dou z multiplied by w minus dou z upon dou t r constant minus v dot del r z. This is, we say, equation number 7. Now we have to use these all equations in this derivation. So this dA upon dt is this, and now we will use this equation 3 for dou A upon dou t, and equation 6 for this, and equation 1 from this. So this will become like this, and this is finally written upon dA upon dt, on dou A upon dou t r constant plus v dot del r only horizontal component into A plus R dot dou A upon dou. Okay, because the rate term will be R dot. You remember, this is equation 7, R dot is this. So the rate terms here are R dot, and so this is the equation. Now we will derive the equation of continuity in generalized coordinate. So 1 upon rho d rho upon dt plus del dot u is equal to derive the continuity equation. This can be written as 1 upon rho d rho upon dt plus vz dot v, that is the horizontal component of this u, plus dou w upon dou z. Now this is d upon dt logarithmic of rho plus del z vertical in z coordinate, horizontal divergent in z coordinate, plus dou omega upon dou z is equal to 0. This is equation 9. And this again from equation 7, and this we will get equation 10 here. That is the derivative with respect to partial derivative with respect to r of r dot. And finally, when we put 10 and 9, we will get, so these terms will cancel out because this is multiplied by dou r upon dou z, so and dou r upon dou z, so this will cancel out. And finally, we will get this equation 11, d upon dt ln dou rho upon dou r plus dou r dot e del r dot b plus dou r dot upon dr equal to 0. So now, so this is still, it is in a generalized coordinate we have got. Now we will be using how to use this equation 11 to get the in isobaric. So this system we used pressure as the independent vertical coordinate instead of height. So now the any atmospheric variable is a function of x, y, p, and t. So when pressure is used as a vertical coordinate, horizontal partial derivatives must be evaluated holding p constant on isobaric surface. Now z increases vertically upward, but p decreases, pressure coordinate p decreases vertically upward. So when w, that is dz upon dt, is greater than 0, we call the rising motion. But dp upon dt, if we denote as omega, so this will be negative, less than 0 for rising motion. So this is the difference in w and omega. So for omega, if it is negative, means rising motion. For w, if it is positive, then it is rising motion. So now, if we equation 11 we have derived, if we put there, before that, if you put r equal to p, then dou rp is equal to dou pp is equal to 0, and dou p upon del rp is equal to del pp is equal to 0, and dou p upon dou p, that is dou r will be p, so it will be 1. So continuity equation 11, we will get this equation. Finally, dou u upon dou x plus dou v upon dou y plus dou omega upon dou p. So this is the continuity equation and isobaric coordinates, which is free from rho. So this is one benefit of isobaric coordinates when we are solving, finding out the vertical velocity and other things. This will can be used. Now, since synoptic scale vertical motions are difficult to observe or diagnose, so we desire a conceptual model to help diagnose and interpret synoptic scale vertical motion from horizontal analysis. So this equation can be used, and we get dou omega upon dou p is equal to minus dou u upon dou x plus dou v upon dou y at isobaric surfaces. So this is what this can be used for deriving of vertical velocity, vertical motion, but it has to be used very cautiously because if there is one order error in evaluating in this divergence, there will be two order error in the evaluation of omega. So that, because scale analysis, which is not here, we are not doing, but then we do that omega is much less than u1. Now we will come to Dine's principle. So integrating downward from the top of atmosphere, so top of atmosphere P is equal to 0 to some pressure level, the previous equation will be omega at P, that pressure level will be minus 0 to P dou u upon dou x plus dou v upon dou y delta P. So thus the vertical motion at a given pressure level is directly related to the integrated divergence above that pressure level that we have seen. Now, the positive integrated divergence means divergence. There is actually divergence, so that will be positive. This will yield negative omega. And as we have seen in the last slide, negative omega means rising motion. And when negative integrated divergence means dou u upon dou x plus dou v upon dou y will be negative, means it will be convergence. This will yield omega greater than 0, that is sinking motion up that level. So what happens below the pressure level? So that we have computed this level P, what will happen below that? So the divergent at upper levels, if it is, that is typically accumulated by convergence accompanied by convergence at the lower levels. And if there is a convergence at the upper level, this is typically accompanied by English meteorologist William Henry Dine. And this states that winds converging on a given column of air at one altitude tends to be balanced by winds diverging at another altitude. And so this is, you can see conservation of mass. If you see that column, so if from somewhere winds are, air is entering, it has to go out from some other level. So therefore the mass will be balanced. So this you get from equation of continuity, that if there will be converging motion, then there has to be a diverging motion in another altitude. So thus the divergence must change its signs at least once in a column. So if upper level divergence, then that has to be accompanied by lower level convergence. Then what will happen? Upper level will be divergence, lower level will be convergence. So it has to change, it has to be 0 at some point. Then only it will change its signs. Because divergence, for divergence, dou u upon dou x plus dou v upon dou y has to be greater than 0. And for convergence, dou u upon dou x plus dou v upon dou y has to be less than 0. So at one place, upper level it is greater than 0, lower level it is less than 0. So somewhere it has to be 0. Then and upper level convergence, that has to be accompanied by lower level divergence, and then at mid level between these there will be subsidence. So this is actually we can see level of non-divergence. So what will happen if dou u upon dou x plus dou v upon dou y is equal to 0? Because there is no, suppose there is a level at which dou u upon dou x plus dou v upon dou y is equal to 0. So that level is called level of non-divergence. And if that will be 0, then dou w upon dou p, dou omega upon dou p will be 0. So it means either it will be maximum or minimum somewhere in the vertical motion. So either maximize existing in vertical motion or minimize existing. So maybe there may be many maxima minima in the modern case in this condition. So now if we see here, so suppose there is a low level in the right hand side, there is a convergence in low level. So what is happening? This is left hand side, the negative is here, positive here for omega. So initially at surface omega is 0. Then it will start decreasing, okay? Because there is a convergence. So omega has to be negative. So it will start decreasing, and at some point it will be the minimum. That is the level of non-divergence. And typically it is around 500. And again it starts increasing and will become 0. Then there is a divergence. So this is low level convergence, upper level divergence, and in between. So you see in the right hand side, this W is this arrow in the middle. So when we are coming at around 500 millibar, the W is arrow is very big. So it is a big increasing motion, rising motion. Okay, so omega will be minimum means negative, maximum negative. You can say minimum means maximum negative. So then there is a rising, maximum rising motion at the level of non-divergence, and again this omega will decrease and become 0. And at the low level divergence, so here winds are diverging. So what will happen? Omega will increase, okay, and it will become maximum positive, and it will decrease and become 0 when there is a convergence. So this maximum omega, maximum positive value, that is called the level of non-divergence, and minimum this omega, that is also called level of non-divergence. So this is what we have seen: level of non-divergence, Dine's compensation principle, equation of continuity in Cartesian and Isobaric coordinates, and all those things. So thanks. This is what.
Thank you, sir. Before we go to question answer session, I would request everyone to switch on their cameras so we can take a photo. Dr. Mohan Kumar Tyagi, sir. Dr. Divya, you want to take some pictures?
Yes, ma'am, I will take, yeah.
Okay. Okay, done. So now I request Dr. Divya to please moderate the question answer session.
Yes, ma'am. Thank you, ma'am. Thank you, sir, for delivering very nice and informative session. So as I can see, ma'am, there is no question in chat box.
Yeah, they have
So,
two of them have written it was a very nice presentation and elaborate. So
yes,
probably.
yes, yes.
So participants, if anyone wants to ask question right now or you want to mail later, it's fine. But if anyone wants to ask right now, you can type in the question answer box.
Yeah, Ronnie, it was more mathematical thing.
Yes, sir. Yes, sir.
Maybe
Yeah.
that's why they are confused. Yeah.
The level of presentation is very high, so students are not able to, I think. So still, any participant have any question, then please ask. Please write your question so that we can ask and we can take that question.
Yes. So should we go to vote of thanks? Maybe after vote of thanks. Oh, there is something. Please suggest some reference books.
Yeah, I will send emails.
Okay. Okay. So
But
thank you.
basically, Holton's.
Holton, yeah, that was right. So,
Okay, so I request Mrunal to conduct vote of thanks.
Yes, thank you, ma'am. I will just share my screen. So thank you, Rohini, ma'am. So on behalf of the organizing committee, I would like to thank each of you for your contribution on this 10th lecture of weekly online series of atmospheric dynamics and its application on climate science. Firstly, I would like to thank AVM Professor Ajit Tyagi for giving welcome address and brief information about this lecture series. My deepest appreciation goes to our speaker of a day, Dr. A.K. Sahai, retired from IITM, for delivering very informative lecture on equation of continuity in Cartesian and Isobaric coordinate system, Dine's compensation principle, concept of level of non-divergence. I also thank Dr. Rohini Bhavar for moderation of today's session and Dr. Divya Prakash for efficiently managing question answer session. I also want to thank all panelists and EC member for their guidance and constant support for every minute detail. I extend my thanks to all the participants and attendees who joined us from various countries. Last but not the least, sincere thank goes to team members of Savitribai Phule Pune University involved in organization of this lecture.
Thank you, Mrunal.
Thank you, ma'am.
So before we go to the end, I would like to give some statistics. Till now, around 139 participants have given their attendance, out of which 123 participants have rated it as excellent or very good. So definitely with your elaborative derivations and all, sir, they really understood what the thing is, though the questions were not there.
Okay, thank you.
thank you so much, sir.
Thank you. Can leave now?